Okay, but today is also a very important lecture because we are going to talk about how we can treat interactions between particles. And this is a very generic concept, does not only apply to solid state physics, applies to all kinds of physics and other branches of science. And it's this idea of mean field theory, which is an approximation to treating full system of interacting particles. You know, we can treat exactly an interacting pair, two particles, like a molecule, like we already saw at the beginning. You have bonding and anti-bonding states in a molecule. You can pretty much solve exactly if there are two particles. There are more particles, it becomes exponentially difficult to solve the full Schrodinger equation. And the exact solutions are often unavailable. Oftentimes, even numerical solutions are difficult and require some approximations. And that's because in the wave function, you have so many degrees of freedom, so many possibilities that you have to sort through to find if that's a solution, that all the atoms in the universe are not enough to explicitly model a system of just a few hundred spins. It's pretty much, spin up and spin down to the power of a few hundred is a huge, huge, huge number. And so this is a fundamental problem. That's why we are building a quantum computer. That's one of the motivations to just have a quantum system and let them interact and see what the answer is. Measure the ground state, measure the spectrum. So one of the motivations is to solve many body problems. But mean field theory is a viable approach in many situations, although it is approximate. And we are going to use magnetism to see how that concept applies. So even though this is the last lecture on magnetism, the important part is maybe not even magnetism itself, but mean field theory. But we are still on ferromagnets and anti-ferromagnets. The phenomenology of that we've covered last time. And now we are going to try to solve a model which generates ferromagnetism. What does it mean to solve a model? It's to write down a Hamiltonian and then to calculate the statistical mechanics properties of the solution. So, for example, if we are talking about a system of spins, then we would be interested in the magnetization of this system as a function of system parameters such as external field and temperature. So we're looking for magnetization as a function of temperature and field. We can calculate susceptibility from this. So this will be our goal. And the first model that we consider is a very powerful model, which already is difficult to solve, even though you will see it's a very simple model. It's called the Eeehm model for interacting spins. So first of all, this model can include magnetic field, and therefore spins are going to have this Zeeman term in their Hamiltonian. So this is just G mu BB dot sigma. That's the energy spins get in the magnetic field. But now here is one of the features of the Eeehm model is that we set the field direction fixed. We say field is always applied in the z direction. And then there are, as you know, two possibilities for what spin can be. Spin can be pointing up or pointing down. And then for the Eeehm model, we remove this vector dot product between b and sigma. And we just write the whole model in terms of just the numbers sigma L, for L being the Lth spin in a chain or on a lattice or in a 2D lattice or a 3D lattice. Actually, you can write Eeehm model in 4 dimensions. Doesn't matter. So L is just an index of a spin, and sigma L can just be +1/2 or -1/2. Those are the two allowed values. We don't consider other projections of spin on other axes and so on. So sigma L is just a set of two numbers. And now we have to add interactions to our Hamiltonian. So we have the Zeeman part here. The interaction term looks like this. So there are terms like sigma I times sigma j. So those are two numbers that can be plus 1/2 or minus 1/2. It is like flipping a coin at each side, right? Two values, nothing in between. J here, this constant j, is the coupling constant in the Eeehm model. I already showed you j last time, but did not solve anything. I just motivated it for you that, of course, when j is larger than 0, then all spins want to line up in the same direction, and you get a ferromagnet. In this formula, if we stick to the same formula, and we can also say when j is less than 0, then it's an antiferromagnet. So in one formula, we have ferromagnet and an antiferromagnet. Right? But we are not interested today in this ground state, which is kind of obvious to figure out just from the sign of j, whether all spins are up or whether they're anti-aligned. That's pretty easy. We are interested in this thermodynamics, right? Being able to calculate quantities like the magnetization. Another important feature in this formula is these triangular brackets here. I think that's maybe explained in the next slide. No. So these triangular brackets mean that we sum only over neighboring spins. So that's one of the assumptions of the model, that interaction between these spins is perhaps dipolar, so two magnetic moments coupling to each other, dipolar interaction, and that drops off pretty fast. In any case, if there are higher order terms, we could include them. That would make things quite a bit more complicated, but for today and for many, many calculations, we only include nearest neighbor spins. And that is also why there is this factor 1/2 in front of j. That's because if you just run over nearest neighbors, this sum will have a term ij and also a term ji. And so we're double counting the interactions. And so we divide it by half, by 2, to make sure we're not double counting here. Okay, so this is the Eeehm model. Here it is put together, the two terms, the Zeeman term and the interaction term, for Eeehm j. And this looks like a very simple Hamiltonian. Turns out not so simple to solve. So it's called Eeehm, and in the United States many people say Eeehm, but he was German, so I guess his mom called him Eeehm, or I guess maybe she called him by his name. Anyhow, he moved to the US, and so he became known as Eeehm. But he was actually a graduate student, and the Hamiltonian was put forth by his PhD advisor. But then he said, okay, you solve it, and Eeehm solved it for his PhD thesis. So that's, but only solved it in one dimension. And what I mean by solved, I mean analytic solution without any approximations. He actually solved it. So it is possible to solve it in one dimension. It is actually also possible to solve it in two dimensions. It took another 20 years after he did it, but then Lars Onsager did it in 1945, just after the war. He solved it explicitly, analytically, write down a solution for this Hamiltonian in two dimensions. Took 20 years. It is, I believe, either impossible or very impractical to solve it in 3 dimensions. Because you can try to do it numerically, or you can use an approximation, and that's what we're going to do today. So with an approximation, I can solve it for you in 5 minutes. Okay. So that's the power of this approximation. It's a mean field theory approach. Okay. So what is this mean field theory? Basically, if you look at this cartoon, you single out one spin or one subset of the system. In any case, could be several particles, but in this case, we're going to have one spin, and then treat interactions with all the other systems. Well, if we only treat nearest neighbors, there are just a few around here, but in principle, treat the rest of the system as some kind of a potential field, magnetic field or electric field, some kind of a potential that this single particle sees from these other particles being around. And so, in a sense, averaging over all these interactions to get an effective field. And this is why it's called mean field, because it's averaged over interactions. So that's the concept, the picture to have in your head. Now, what is specifically done by people when they write down a mean field theory? It is these two steps, and both of these steps are crucial, very important for the model to make actual sense in the end. So the first one is like I described to you. In your Hamiltonian, you have operators, like sigma operators, for example. And then for the mean field approach, you are going to take the averages of some operators in your Hamiltonian. And you replace the actual operators with their averages. But then the second assumption, without that, nothing works. So this is really, really important, that if we focus on this blue spin, we can assume a certain average field. But then if we move over and, let's say, select this spin as the blue spin, then nothing should change. We should get the same average field. And this is called self-consistency. The theory has to be self-consistent. And in a moment, I will show you what that means in terms of an actual equation. And it will become more clear. But for now, just have this picture in mind. Why is this important? Because, well, we need some kind of criterion to know that the average field that we chose is the one that correctly approximates the interactions, right? And so this is why, at least by moving around, you should get the same result regardless of where you are. And like I said, this is a procedure that can be applied to all kinds of systems, especially when there is a large number of particles, and then averaging becomes especially a good approach. This particular version of the mean field theory is called the Weiss mean field theory, after Weiss. Okay. So let's start approximating. Once again, this is the Ising model Hamiltonian. They're actually not due to Ising, but he solved it, like I said. But we're going to solve it approximately. And so the first thing we're going to do is, like I said, we're going to focus on one site, the blue site, and that site is with a label I. So we're going to take that spin out of the formula and write the Hamiltonian for that spin I. So it will have this Zeeman term where you just have sigma I in that term. And then it's going to have this sum that runs over all of its nearest neighbors. So now the factor 1/2 disappeared in front because we are not double counting anymore. There's one I, and we just go around, and this sum contains all of the nearest neighbors. So Ni is a set of nearest neighbors. So this is just a part of the Hamiltonian that concerns spin I. And here is the approximation. This Hamiltonian Hi is approximately this Hamiltonian. You can spot the difference. Right, so these brackets here. We are going to average all the expectation value, all the operators for the nearest neighbors, right? So we replace the operator sigma j with the expectation values of those operators. Right? So some average spin on those sites. Now, we don't know what that is because of these interactions, right? This average is not 0, for example. Right? It doesn't have to be 0, right? Otherwise, you would never have ferromagnetism. So if there's ferromagnetism, this is not 0. Right? So there are some non-trivial situations where this is not 0, and that's thanks to interactions between spins. All right. So here comes self-consistency, or the beginning of it anyways. The expectation value for sigma j is the same as the expectation value for any spin on this lattice. So we can also replace sigma j with sigma I. So the expectation value of sigma I. And this is what we're doing here. We are replacing, so sigma j becomes sigma I, or the expectation value. And then this sum over these expectation values, they're all the same. So the sum just becomes z, which is the number of nearest neighbors, times the expectation value of sigma I. So all the terms in the sum are the same. They are all the same as sigma I because of the self-consistency of the mean field approach. And there are z terms in this sum, so it's z times sigma I. And this is what's written down here. And this is also what's written up here. So here is, I want to make another conceptual statement. If we define B effective here as being such field that HI is equal to G mu B B effective sigma I, right? Then we see that we take this second term that has JZ in it, and we say JZ sigma I is equal to G mu and some kind of B star. Then we can define a field which is not a real field, which is not a real external field in which the spin sits, but it's an effective field due to interaction with other particles. So in my definition here, B effective is going to be B minus JZ sigma I G mu B, right? See, this is going to be the effective field from this. So this field is a result of applying this mean field theory. So we averaged all the interactions with other spins and represent them by this field B star, which gives us the effective field B minus B star, or B minus this JZ sigma average over G mu B. So there is an effective field due to averaged interactions. Okay. So now we can do actually statistical mechanics with this Hamiltonian, because this is just a very simple Hamiltonian, G mu B B effective sigma I. So we know that for any B effective, there will be two eigenstates, spin up and spin down, according to this field B effective. And we've already done the statistical mechanics of this spin 1/2 system in a magnetic field or at finite temperature. So this now becomes easy. But for the beginning, let's actually put the real field B to 0, right? So B effective will still be non-zero, but B, the external field, is 0, right? You know the difference? So this term goes to 0, but this second term with Jz is still there, and it gives a Zeeman splitting. So the eigenstates of this Hamiltonian with B effective will be plus minus Jz over 2 sigma I. So we know exactly how to solve this. There are two states, two possibilities. So the partition function for this has two terms which contain the respective energies that we just found. And then the expectation value, the sigma I, is a function that has the difference of these terms in the upstairs and the partition function in the downstairs, right? So this is just a reminder, average will be the one value, say 1/2, times exponent of the energy of that state 1/2. So beta E minus 1/2 e to the minus beta E divided by z, the partition function, right? So that's the expectation value for a two-state system with spin up and spin down. So the eigenvalue, then the exponential term, and sum over all eigenvalues like that. So this has a very nice symmetry because exponent minus exponent divided by exponent plus exponent gives a hyperbolic tangent function. So the solution is actually very elegant. The expectation value is equal to 1/2 of this hyperbolic tangent function. Right? So we're done. In principle, yes, we are done. But this equation has a complication. Right? Who can point out the complication with this equation? Can you write down a solution as a formula for this equation? Why not? It's a transcendental equation, right? So you have this expectation value of sigma I on the left side, and you also have it in the hyperbolic tangent here. So it's a transcendental equation. Yeah, we can solve it numerically, for example. So there is a solution. It's no problem. But it's actually very illustrative to solve it graphically. So we're going to do it graphically. So the way we're going to solve it is we are going to plot the left-hand side of this equation as a function y equal to the expectation value of sigma I. And we are going to plot on the same graph another function which is the right-hand side of this equation. And those are the red and the blue curves on this graph. So this axis is y, and this axis here is sigma. And a solution, obviously, to our equation is when two of the graphs cross each other. Right? So there is always a solution, it seems, at sigma equals 0. Sigma equals 0 means no polarization. Right? This method always gives that solution. And then, depending on temperature, actually, you can have more solutions or not. So let's first look at a very large temperature. So that's here, T large. So when T is large, beta is small, right? Remember, beta is 1 over kBt. So beta is small, so the hyperbolic tangent ramps up only very gradually. And so this is this situation where the blue function never crosses again the red line after leaving sigma equals 0 point. So this is a situation for large temperature. And so in this case, polarization is 0 at 0 magnetic field, right? Remember that we are at B equals 0 external field, B equals 0. We have this effective field due to interactions, but external field is 0. But then if temperature is small, this hyperbolic tangent function becomes rather steep. And it actually crosses the red line in 3 places. And sigma equals 0 is the trivial solution here. But there are also these 2 other positions. And they are symmetric. And they correspond to a finite magnetization. And there can be a positive magnetization, and there can also be a negative magnetization. Right? So if you think back to the ferromagnet, how we discussed it, yes, at 0 external field, the ferromagnet, they can all point up or they can all point down. And there is no way to distinguish which way it's going to go a priori. Right? So there are 2 solutions for polarized up and polarized down. Now you can also see that as the function gets steeper, this crossing point will move around. And when the function is very steep, it will actually go to this 1 on this scale here, which actually corresponds to the, because there is a 2 sigma here, so this corresponds to actually 1/2 sigma. Right? So 1 corresponds to 1/2 here. So that means at very, very low temperature, the magnetization, the expectation value of magnetization will be 1 plus 1/2 or minus 1/2 at each site. So all the spins will really be aligned. But at any finite temperature, this crossing point is not quite reaching that 1, that saturation level. And that means that at finite temperature, some of the spins will not be pointing all in the same direction. Right? So some of the spins will be pointing in the other direction because there is some thermal energy in the system that allows them to flip and not be in their ground state. So this is just all the apparatus of statistical mechanics that makes all of this very reasonable. That tells us that these are all as expected. Okay, so then the next question is, when is the first temperature at which these extra solutions develop, right? So here we have 1 solution, here we have 3 solutions. What are we doing here? We're lowering temperature. So as we lower temperature, there must be 1 temperature where it just starts to develop these extra solutions, and that's called the critical temperature. That's also the phase transition temperature, right? So when you start having finite magnetization, that's called the critical temperature. And how do we find the critical temperature? Well, that's easy. We need to find where the slope of this hyperbolic tangent just matches the slope of the red line. It's just equal to sigma z expectation value. When that happens, at that temperature, we have this transition into the polarized or ferromagnetic state. So we can easily calculate this if we assume this. So for small arguments of the hyperbolic tangent, then we approximate it like this. And this then must be equal to the slope of the red line, which is sigma I expectation value. And this tells us that 1 over beta is equal to jz over 4. So 1 over beta critical, or Boltzmann constant critical temperature equal to jz over 4. So that's the critical temperature below which the system will generate magnetization at 0 external field, just due to interactions. And above that temperature, thermal fluctuations, thermal energy is large and exceeds the energy gain due to interactions. So actually I had it all derived for you here on this slide. So this is again the same formula, critical temperature expressed in terms of Jz. Pretty much the meaning of this critical temperature is very easy to see from this formula. So you have Z times J couplings to neighboring spins. When you have temperature, thermal energy that exceeds that, when you have more thermal energy than the couplings to all your neighbors, that's when ferromagnet is destroyed. So this is the meaning of this formula. It was a little bit hasslesome, is that a word, to derive this, but in the end, the meaning of this formula is very, very transparent. So take one spin, all its neighbors' couplings amount to Jz, and when the thermal energy is higher, then you undergo this phase transition out of the ferromagnetic state. Okay. Then we can also calculate either numerically or by plotting this graph a bunch of times and reading off the magnetization of the plot. We can calculate this magnetization or average spin per site as a function of temperature. And turns out that it does something like this. So it actually fairly flat away from TC. So that's where all the spins are pointing really in the same direction or almost. And then it starts to gradually go down and then dramatically crashes at TC. So this is the x-axis here is normalized in the units of TC. So at TC, at this critical temperature, magnetization goes to 0. And then above that, it stays at 0 forever up to infinite temperature. And once again, remember, this is at 0 field. So if we apply field, then of course we can also have magnetization here because we have all these spins. Each site has a spin in the Eeehm model. Right? We are still in the Eeehm model. Each site has a spin, and we can certainly polarize them, magnetize the system with an external field. So importantly, this magnetization happens without any external field, right? Just due to interactions. So now there is also this important concept associated with such kind of phase transitions. It's called symmetry breaking. This is just representing this fact that at very low temperature, all spins can align up or they can all align down. But if you look at a specific piece of ferromagnet, you will find only one or the other. Right? In this Ising model, we're not considering domains at this point. So this is a chunk of space filled with spins, and they will all be pointing up. We don't consider the physics of domains here. They will all be pointing up, or they will all be pointing down. But what determines what they do is this concept of spontaneous symmetry breaking. And we can understand it as some little fluctuation in the field, maybe a passing truck as we cool the system down, or a little bit of field from your cell phone that will break the symmetry and tip the system one way or the other. And an infinitesimally small such perturbation can do that. So spontaneously the system is broken. The way we can see that is by plotting the free energy of the system. So you can use the thermodynamic definition of that, which is just a logarithm of the partition function. Or I can also motivate why the function should look like this. But in the view of time, I just want to tell you that if you do this, these are the graphs you're going to get for the free energy of the system as a function of sigma magnetization. And this is, once again, in zero external field, or nominally zero, close to zero. And the two curves are above TC and below TC. You see, this one is above TC, and it is just a symmetric parabolish-looking dependence. And it has only one minimum at sigma equals 0. And so that's going to be the thermodynamic solution of the system. Even if you somehow generate magnetization here, the system will want to minimize its free energy, and you will find it down here after some time. Okay. And this is in stark contrast with what happens below TC, and fairly far away from TC. You have these two minima, and one with negative sigma, one with positive sigma. By the way, both curves have an extremum point at 0, right? So for the double well potential, for the double well energy landscape, there is also this point 0 where the derivative is 0, but it's a maximum. So it's not a stable configuration. And this is connecting nicely to the solution of the transcendental equation. Remember, there was a solution at 0. So where we plotted sigma, and we had a straight line, and we had, sorry, this is supposed to be 0 here, and we had the hyperbolic tangent. They were always intersecting at 0. So that equation was giving us this solution with sigma 0. But from the energy landscape, we see that that is actually a local maximum. That is not a stable point. So if you put a system here, any tiny, tiny perturbation will break the symmetry, and you will find the entire system, all the spins, tipping either one way or the other, spontaneously. And this is the symmetry breaking story that always happens. So you can also imagine a little ball sitting on top of a big spherical surface, right, on top, and then wind blows, and the ball can end up in dramatically different directions depending on a small gust of wind. That's the same analogy. Okay, so this is a bunch of words to the same effect, I believe. So for t greater than Tc, there is one solution with sigma equals 0. For t less than Tc, actually, the solutions are with sigma not equal to 0. And you can see that from the free energy of the system. Even though we did not derive it, it is still intuitively clear that it should look like this with two minima. So spontaneous symmetry breaking is a fundamental concept that you can encounter in other branches of science, like I said. And in condensed matter, it could be this very small stray magnetic field that tips the system. Now, another way we can guide the system into one minimum or the other is by explicitly applying an external field ourselves. So this is how ferromagnets are actually, permanent magnets are created. That's how they're trained. So you go above Tc, and you're in this situation. from the point of view of free energy, but you are applying a magnetic field, and so you shift this distribution, and you basically end up on one side of the distribution. But I have to plot another term from magnetic field to see that it wants to be there. There will be a slope from field, right? Because field is like adding g mu b sigma to this situation. So there will be a linear slope, and minimum will shift from 0, left or right, depending on the field. But then you cool through the transition, and you are on this side, and you're going to end up in here as you cool through the transition. So this is, again, sigma. This is free energy. Here we have to add a linear term like this to the parabola. And it will shift in one direction. Right. So in the case of the ferromagnetic situation, you can make one of the minima higher than the other by applying a magnetic field. But if you are already in the ferromagnetic regime, the fact that one minimum is higher than the other is not enough to flip the system, because there is this tunneling, there is this barrier in between, right? So you need to overcome the barrier. So to flip a ferromagnet, you actually need to go to this situation such that one minimum becomes flat and the particle can roll out and go here. And this is also another way to see why there is going to be a hysteresis in this system. So you have to go to a large field in that direction, before the system will flip from pointing that way to pointing that way. And on the way back, you're going to have the same story. You're going to have to go all the way to here before the system flips. And so this is, from the energetic point of view, this is how hysteresis appears in these systems. Okay. Okay. The same math with the Eeehm model we can do with finite field applied, and this is an exercise. It's actually fairly easy to do, so I'm going to try to do it with you on the board. So we considered b equals 0 so far, and only qualitatively what happens at finite field. What about b greater than 0? Well, we're not going to derive it, but I think it's pretty easy to show that the transcendental equation that we're going to have to solve is going to be just like the old one, but there is going to be this b term here. So the magnetic field is not 0. So there's going to be this external term here. So what will be the magnetization? We can make the same approximation that temperature is very large, so beta is small, and therefore the hyperbolic tangent is just pretty close to its argument. So hyperbolic tangent of x is approximately x. And then this equation becomes expectation value of sigma equal to, so all the minus signs here will cancel if we remove this hyperbolic tangent, and we're going to have beta g mu b divided by 2 plus j z sigma divided by 4. That's just opening the brackets here. And then we take the term with sigma and put it here. And we also remember that Tc is, Jz divided by 4 kb. And then it's gonna, this equation is gonna transform like this. expectation value of sigma 1 minus, sorry, one minus Tc divided by T, and this is equal to, if we substitute G equal 2 for simplicity here, then we're going to have mu B, B divided by KB T. Now, to go from sigma to magnetization, we have to make it M equal to the density of spins times Bohr magneton times sigma. So this is how we go from spin value to magnetization. Each spin gives you a Bohr magneton of magnetic moment, and then the density of spins gives you the amount of magnetic moment per unit volume. So you have this magnetization, and when T is much greater than Tc, so we are way above the ferromagnetic transition, then we can neglect this term in brackets. Tc over T is very small, and magnetization is just equal to n mu B squared B divided by KT. And this result is actually the result for Pauli paramagnetism. If you remember, this is when we consider magnetism of just free electrons with a polarization. Magnetism of non-interacting electrons with just some magnetic field on. We got this formula with the 1 over T dependence. We called it the Curie Law. Now, if we don't make this approximation that T is much greater than Tc, then we're going to have to drag around this 1 over 1 minus Tc over T. And we will see that spin susceptibility, which is dm by dB. So we just take a derivative of this m with b, and b just disappears from the formula. That's very easy. But there is this denominator of 1 minus Tc over T that is left over. So what is significant about this formula is that it diverges when T is equal to Tc. It becomes infinite. So you can see, if I plot the susceptibility as a function of temperature, and this is Tc, this formula is going to give me a divergence right at Tc. And this is maybe also not so surprising because, remember, below Tc we have spontaneous magnetization. So at zero field we have finite magnetization. So we can say that for a very small field, 0, we have constant magnetization, which means that our susceptibility is infinite. You could argue this way. So this is how you can understand this divergence here. Like I told you before, these kind of divergences are often accompanying phase transitions, and ferromagnetic transition is a phase transition, and so in this case spin susceptibility diverges at the transition. Okay, remaining time, we are going to discuss another example of a mean field theory, which is of profound importance. But we are going to, again, motivate this discussion by another case of ferromagnetism, so by a real physical phenomenon that we already know about. This one is called itinerant ferromagnetism, and the difference with the Ising model is that spins are now allowed to hop between lattice sites. So in the Ising model, they were fixed, and then they could just interact by something like dipolar interactions, for example, or some other interactions. But they could not move. And now we are going to combine an interacting term with the hopping term. So we're going to have a tight binding model with an extra term, interaction. Now, why do we want to study this? Turns out that the ferromagnets you think about, like iron, are of this type. So magnetism in iron is created by moving electrons. It's not actually, it's very far from the Ising model. Ising model is a great one to solve. We learn a lot from it. And it describes some materials, but not the most common ferromagnets. They are itinerant. So think about it. Electrons are flying around in a material, yet still they interact and they magnetize spontaneously. So there is still ferromagnetism in these systems, right? And this model that we're going to discuss now does capture that very nicely. First what we're going to do is we're going to review a little bit the physics of electrons that are moving in bands. And what happens when you have, let's say, a free electron gas and it becomes spin polarized. So in this case, let's start with this one. In this case, we have this free electron Hamiltonian with a Zeeman term. No interactions yet, so we are going to contrast this situation to the one with interactions in a moment. But once again, there are two eigenstates which are different by the Zeeman term here. Right? So the two spins have the same momentum, but they have a different energy for the same momentum because of the magnetic field present there. And remember, we were calculating magnetization of this system by saying that it is equal to mu b divided by the volume of the system times number of spin up minus number of spin down. Excuse me. Right? And so a way to visualize this was this diagram. So now you have a dispersion relation with all the states below the Fermi level field. And at zero magnetic field, you have exactly the same number of spin up as the number of spin down. And so the situation looks indistinguishable. The same number of electrons fill to the same Fermi level, this system. And now at finite magnetic field, we had these two parabolas, these two dispersion relations of free electrons shift by the Zeeman term. Because we just derived or just refreshed ourselves with the fact that for the same momentum, you take any momentum here, or that means for the same energy, for the same momentum, energy is different. And so if you plot it in these coordinates, that means there is this shift. One band shifts up, the other band shifts down with respect to the zero field position. And then we still fill the system up to the same Fermi level in both subspaces. And that means you have more of the spin down in this case than of the spin up. You have more of one spin than of the other. And that means you've magnetized the system. This is paramagnetism. Right? This is paramagnetism because at zero field there is no net magnetization. At finite field there is net magnetization. From the sign of it you can work out that this is actually paramagnetism, not diamagnetism. Okay, and then the susceptibility of this system was actually independent of temperature, right? As opposed to the Pauli, as opposed to the one we just discussed, which was Curie, which was 1 over T. That's for spins that are not interacting. And these ones in the living in the Sommerfeld gas, so in the free electron gas, all of them at small energy are packed and they cannot flip their spins because they're so far from Fermi energy, and only the ones in the very small vicinity of the Fermi energy can magnetize and demagnetize. And so because there is a much smaller number of spins participating, the energy interval of order kBt, so kT of spins around Fermi energy are participating in this, then that cancels the 1 over T dependence, and we have a constant spin susceptibility. So this is with this story without interactions for free electrons, electrons that are free to move. Now with interactions, we are going to consider a version of the tight binding model, which is called the Hubbard model. This model is extremely significant, maybe even more significant than the Ising model. So it is expected to generate all kinds of exotic phases, including most prominently high temperature superconductivity, supposed to be produced in this model, but nobody can solve it. So it's extremely difficult to solve, even with a supercomputer. You cannot solve it very well. Anyways, it is a very simple model. As you will see, the Hamiltonian is very simple. And it is our tight binding Hamiltonian. Remember, we had hopping J between sites. And this is now a little confusing because we use J in the Ising model. But now I want you to forget about that J. And here, this J is from the tight binding model. And that described hopping from one side to the next in a lattice. Right? Remember, we had orbitals on each lattice side, and we could hop between them. And that was described by J. And that model gives us the band structure, right? Remember, that gave us the cosine-like bands when we solved that tight binding model. We got the cosine bands. However, there was nothing interesting about spin that we could learn from that, because we need to include these interactions to generate something like ferromagnetism or anti-ferromagnetism. And this is how you add interactions. So you basically say that you have to pay an energy for 2 electrons to be on the same site. That's proportional to U. So when 2 electrons are on the same site, they must have opposite spin. Otherwise, Pauli exclusion principle would not allow it. And so you have a number occupancy of site I for spin up times the occupancy of site for spin down. And so what the possibilities here, Ni and up and Ni down can be both 0. Then you don't pay anything. Ni can be 1, Ni up can be 1, Ni down can be 0. Then you don't pay anything. But when they're both 1, then you pay energy U. So you are penalized for putting 2 electrons on the same side. So they can hop around, but if there are 2 of them on the same side, you can do it, but you have to pay this energy. If you have this energy, you pay it, and you put 2 electrons on one side. If you don't have it, you cannot put 2 electrons on the same side. So that's the Hubbard interaction. Okay, so first we consider it very generally, so U and J can be also of comparable value. We can first think about what happens if none of the electrons are sitting on the same site. So each electron sits on its own side, or maybe you're less than half filling, some sites are missing. In any case, you don't pay this energy U anywhere. Then in this case, you will see that it prefers to have all the spins polarized. So interaction energy is 0, but all the spins prefer to be polarized. And magnetization will decrease because, magnetization will be high, but susceptibility will be fairly low. So this is already one way why interactions favor magnetic order. So if you imagine that electrons are repelled from each other, then they all want to align in the same direction. But if you do that, if you put all spins pointing in the same direction, you pay another energy here. So there is a trade-off. So you minimize the interaction energy by putting them all far apart from each other, not on the same side. So you don't pay U, but you don't get away so easily, because this has implications for the kinetic energy. So for the hopping part of this Hamiltonian. And this is how it comes about. So once again, this is our starting point, a free electron gas, or now we can say that this is the band of the tight binding model. Doesn't matter for this discussion. Same number of spin up and spin down because magnetization is 0. Now let's say we want to put this system into a ferromagnetic state, or in any case in a state with non-zero magnetization at 0 field. So at 0 field means there is no shift in these parabolas. There is no the Zeeman shift of the parabolas. They all start at the same point. But here you have more electrons in one spin orientation than in the other. And so you have this extra energy in one department that you have to pay. And if you keep making this story more and more dramatic, more and more polarization, you have to pay more and more kinetic energy to sustain that state. And so infinite polarization is not favorable here. So some polarization can be okay, but not infinite. So kinetic energy puts a boundary on how polarized you can be in this Hubbard model. Okay, so how do we solve the Hubbard model? Like I told you, you can't. You can't solve it. It's too hard. So we have to use a mean field approach. Okay? So to use a mean field approach, we have to replace some operators with their averages. And this is what we're going to do. We're going to take this Hubbard interaction term, and first we're just going to algebraically rewrite it in this form where we have the sum of the two occupancies and their difference. So what's the physical meaning of these? The sum of the two is just the density, just the number of particles. Right? Sum of all the spin up and spin down, that's just a number of particles, and that's fixed in the system. You know how many particles you have. So this first term will not be very interesting, and it's going to give us some kind of a constant. The second term is the difference. So what is that? Difference between up and down. That's the magnetization. Right? That's the magnetization. So that's proportional to the magnetization. Now this is still explicit, and the second line in this red frame, that's the mean field approximation. So here we're making an approximation that this is approximately equal to this averaged expression. Okay. So the rest of the idea is very similar to the other mean field approaches. Like I said, the first term here is just the density, and that's fixed. Average occupation of up and down is just density. The second term is magnetization, so we can just replace it with M, the magnetization of the system. And then the expectation value of this operator in terms of M and N, the density, is just this expression. This is just substituting N and M into this formula. Okay? This is doing nothing else. But that tells you that if we just, we call this first term H0. This is not dependent on anything magnetic here. So that's just H0. And that gives us the energy E0. Then the difference in energy that the system gains from being at the finite magnetization is just this expression, and it's a negative energy, which means that the system wants to have magnetization. The system wants to have magnetization. Okay? But that is just from treating the interaction term, not the J. Right? We don't have J here, not the hopping. Hopping is not here. This is just to show that indeed, due to these interactions, system prefers to be in a magnetized state. at 0 external field. Now we can also, well, here again, I am going to just give you a formula without deriving it. I apologize. But once again, it's a formula that's easy to motivate. So if we use our definition from the free electron gas for the spin susceptibility, then in terms of this number, this magnetization energy can be expressed in terms of this formula, which has a quadratic term, linear term, and this constant here. And this is a very generic formula. You can convince yourself very easily that it has to look like this. And one way to convince yourself is to check that the system minimizes its energy when dEdm is equal to 0, and in the absence of interactions. This is just for Pauli case. In the absence of interactions, that gives you the magnetization that you expect for the free electron gas. Right? So this is without any interactions. This is the generic form of Eeehm. Okay, so then Eeehm is equal to this formula at 0 field. When we put this term to 0, then we just have this quadratic dependence, and we can substitute all the parameters of the free electron gas here. And if we combine this with the contribution due to the interactions, then we get this net formula. So we combine the term with U and this other term that just comes from them being having kinetic energy and being in an electron gas in a Fermi C. And this puts a criterion for what U has to be in order to magnetize the system. So to have non-zero magnetization, this second term has to be greater than the first term. You're going too fast through this? Maybe. So this term with a circle is due to interactions. And this term is from kinetic energy. And so if you keep polarizing the system, you're paying kinetic energy more and more. And so that is not allowed. And this is the mathematical form of that expression. And that tells you that your interaction strength has to be larger than some threshold in order for you to have magnetization. And this threshold, you can see it depends on capital V divided by small v. That's just a number of particles. So make it simpler. And then it has this F of EF. That's the density of states at the Fermi level. So these basic parameters of the system tell you what interaction has to be. And this is known as the Stoner criterion. And this is a very famous formula in magnetism. But the idea comes from this fact that there's a competition between kinetic energy and interaction energy, and that makes the system polarize. Okay, so a few words about, more words about Hubbard Model. One thing that the Hubbard Model gives you is this Mott insulator. Remember, I mentioned it very briefly. I guess you don't remember, but this is a tight binding system. This is a band, and this is a half-filled band, which means that each side donated 1 electron, but due to spin degeneracy, they're being spin up and spin down, you only fill half of the band, including spin degeneracy, right? And so this system is supposed to be a metal because the band is half-filled and you can occupy all these states. But if U is very large, the interaction term is very, very large. If U is very large, then you cannot do this because you begin with there being one electron at each site, and wherever you try to put 2, you have to pay this gigantic U, and you simply don't have enough energy to do that. And so that system actually becomes an insulator. That's called a Mott insulator. Okay. So this you can get from the Hubbard model. Turns out in a Mott insulator, spins prefer to align anti-ferromagnetically. Not ferromagnetically, but anti-ferromagnetically. And that comes from higher orders in interaction. So you have to include higher orders, and you see that spins prefer to align anti-ferromagnetically. So basically, the reason why this is an antiferromagnet is explained in this slide. It is because there are these so-called virtual processes. Virtual processes are processes for which you don't have energy, actually, but you can borrow it from vacuum, do the process, and then return the energy, and then you can still do it. But then, of course, these processes are very improbable, and so they occur in higher orders of some kind of expansion, for example, perturbation theory. And so they are proportional to this smaller constant, J squared over U. And they make it so that you can that the system prefers to align itself antiferromagnetically. And one example of a Mott antiferromagnet is this very important family of materials, which we are going to discuss a little bit after the midterm. These cuprate materials, they look very complicated. They have these planes in their crystal structure, which are copper-oxygen planes, and they have some atoms in between. There can be various different atoms. And so in part of their phase diagram, they are Mott antiferromagnets. In another part, so you change the doping, you change the proportion of oxygen here, and they become high-temperature superconductors. So they are extremely important materials. They are an example of this system, this Mott system. Okay, I don't really have time to talk about the Heisenberg model, but this is another Hamiltonian which you can solve. And here, this approximation is not made, that spin can only be up or down. We keep the vector spins and the dot product here in this case. And so this is necessary when you talk about this system with higher order terms. So this is a more complicated, but actually more relevant for things like quantum computing. This model is more relevant than the Ising model. This is just a plot that highlights the richness of Hubbard model. I already mentioned it to you that you often see in physics talks this kind of phase diagrams. On this axis you have something called doping. Basically how many electrons you put into the system, how much the band is filled. Is it half filled? Is it less than half filled? Is it more than half filled? And you can do that chemically. You just add some atoms like in a semiconductor. Like in a semiconductor you can dope N-type or P-type. Here you can dope at half filling or away from half filling. So half filling tends to be around here, I believe. And at low temperature, around half filling, you have this superconductivity. And remarkable thing about it is that it reaches very high temperatures. So that's why it's called high temperature superconductivity. You can even do these kind of experiments in liquid nitrogen. Unfortunately, not at room temperature. Right? That would be awesome. And so one of the directions is to figure out why these superconductors do this. It's actually not known, not exactly known why they superconduct, why these materials superconduct, and how can we tweak their chemistry such that we can increase this critical temperature and make it a room temperature superconductor. And for this reason, people are very interested in this Hubbard model because they believe it describes these materials fairly accurately. But it is very hard to solve. Okay, so all these things here, no analytical methods, or they're intractable anywhere away from this one point. And like I told you before, Hilbert space is exponentially large. So the number of eigenstates times the number of sites is extremely large here. So you cannot just put it in a computer. And there is also something called the fermion sign problem, which if you never heard of it, I will not describe it to you in 1 minute that's left. But it's makes it very hard to do numerics with the fermions. Now, let's just look at this diagram some more. Now, this is this part that says Néel order. That's the Mott antiferromagnet. So it's a Mott insulator, which has this antiferromagnetic Néel order, right, after Louis Néel. This is superconductivity, which we will discuss. But look at these other words here. Fermi Liquid, that's kind of the one that we know. So that's something close to the Sommerfeld model. So free electron gas. Actually, not quite. So this is some kind of a not quite that Fermi Liquid. But let's say, okay, we maybe know what's happening here at high temperature and at high doping. So a lot of electrons and high temperature. But then there's a strange Fermi Liquid. So it has some weird properties. There's this pseudo gap regime. It looks from some measurements like it's superconducting, but it's actually not. So all of this is experimentally observed, and people are trying to understand it with this very rich Hubbard model. So, however, Hubbard model is rather successful in explaining itinerant ferromagnetism, and this is what we just discussed with you today. Okay, we stop here.